Hello students, so today I discuss the second part of elasticity. So I have already discussed elasticity lecture 1, this is lecture 2. So today's discussion about Poisson's ratio. What is Poisson's ratio? Take this diagram. First, when a wire is longitudinally stretched, there is a contraction laterally along with elongation along with the length. So when a wire is stretched, so there will be a contraction laterally and also with laterally contraction along with elongation along with the length. So how it's work, like if we take two-dimensional a wire, a cross sectional area of a wire. So now if we give pressure from the above and below, so it will be in this way. So now if we take the lengthwise elongation, this is minus delta L slash, and the contraction laterally we will take delta L. So there are two changes in two-dimensional cases. In three-dimensional there will be three changes. So here axial strain, here the axial strain through x-axis is delta L. Through x-axis this will be after the contraction or stretch, this will be delta L along with the x-axis. This is called axial strain, and the transverse strain is this along with the y-axis. So this is minus delta L dash, because this is decreasing, so that's why the negative sign is introduced. So minus delta L slash is the transverse system. So Poisson's ratio is mu is the ratio of the transverse strain by axial strain. So this will be minus delta L slash by delta L. So this is called Poisson's ratio for two-dimensional cases. For three-dimensional cases, this is senior class, so I will not discuss today. Later, just for the concept of the Poisson's ratio, I have discussed the two-dimensional case. Now, so when we stretch a wire, what is the work done in stretching? When a force acts on a body to produce deformation on it, work is done on the body. The work remains in the body as potential energy, and on the removal of the deforming force, the body remains safe, regains its shape, and this energy is evolved as heat energy. So what will be the potential energy or the heat energy which evolved after the body regains its shape? So this elastic potential energy or work done in stretching is actually equal to half into applied force into elongation. So what is the applied force we apply, and what is the elongation or the change in the shape, multiply half is the elastic potential energy. So it can be expressed in another way also. If we take in this way, a wire length L is hung from a wall, and we have introduced a force F. So the elongation is delta L, and the cross sectional area of this wire is capital A. So here applied force is F, elongation is delta A, and the length of the wire is L. So work done in stretching is equal to, as I have said, half into applied force into elongation. So it will be half into F into delta L. We can rewrite it in this way: half into F by A into delta L by L, and A and A and L multiplied with it. So it will be unchanged. So now this is equal to stress and this is equal to strain. So half into stress into strain, and A into L, A is cross section area and L is the length, so it will be the volume of the wire. So this will be volume of the wire. So if we take unit volume if of the wire, what is the potential energy for unit volume of the wire. So in elastic potential energy per unit volume will be just half into stress into strain. This will be unit 1. So this is the another representation for per unit volume of elastic potential. Now a example I have here given. A mass of 5 kg is suspended from a vertical wire in 1 meter long and of 1 millimeter radius. If the Young's modulus of the material of the wire be 2 multiplied 10 to the power 12 dyne per centimeter square, find the length of the wire without load. So here given that the actually the length after when the load is working, then the length plus the elongation both will be taken together, which is 1 meter or 100 centimeter, and mass is given 5 kg. This is converted into CGS unit 5000 gram, and R is given 1 millimeter, so this will be 0.1 centimeter. So all are changed into CGS units. Now here A is equal to pi r square. A is the cross sectional area of the wire, so this will be pi into 0.1 whole square centimeter square. So we have to find out L, length of the wire, and given also the Young modulus Y is equal to 2 into 10 to the power 12 dyne per centimeter square. So what is the stress here? Stress will be the weight. Here weight is working is the force. So weight by cross sectional area, weight is mg, mass into gravitational force by gravitational acceleration by A is the pi r square. So strain, what will be? Strain will be here strain will be delta L by L. This will be delta L by L. So we are taking here wrong. So this will be actually it will be reversed 100 minus L by L, because L plus delta L is equal to 100 centimeters. So delta L will be 100 minus L by L. So here it is written right. So delta L by L, 100 minus L by L. So Young modulus is equal to W work stress by strain. So this will be in this form. So if we put the values of these values given, then it will be Young modulus is equal to W by A 100 minus 100 by L minus 1. So this will be 100 by L minus 1 YA by W, 100 by L is equal to YA by W plus 1. So this will be YA plus W by W. So what will be L length W multiply 100 by W plus YA. So if we put these values, then we will get by calculator, simple calculation, 99.929924 centimeters. So this is the length, and the rest of to become 100 centimeter will be the elongation. So this is the length. Now the second problem, find the work done in stretching a wire of 1 millimeter cross section and 2 meter by 2 meter length by through 0.1 millimeter. So length is 2 meter elongation is 0.1 millimeter. So Young modulus is given 2 into 10 to the power 12 dyne per centimeter square. So we know that work done is W is equal to half into stress, half into applied force into elongation. So Young modulus Y is equal to stress by strain F by A by delta L by L, and this will be then F will be YA delta L by L. So if we put these values, then we will get here given that A is 1 millimeter square. So in CGS 1 by 100 centimeter square. L is given 2 meter. This will be 200 centimeter. Delta is L is given 0.1 millimeter, 1 by 100 centimeter, and Young modulus is given 2 into 10 to the power 12 dyne per centimeter square. So what will be F? If we put these values, then we will get 10 to the power 6 dyne. So what will be the work? So work is equal to half into force into elongation. So here 10 to the power 6 dyne, and delta L is 1 by 100 centimeter. So this will be 10 to the power 4 by 2 means 5000 R. So this is the work needed to to solve this problem. This is the required work we have to do. So if you like these videos, then like and follow me in YouTube and Facebook, and if you have not subscribed, then subscribe in YouTube. If you are watching my videos and like my video, and share it with your friends.